It's a good evening to meet and share a webinar along with you. And I hope there are many registrant viewers who are also looking at this webinar. So for one and all, I wish my best of your learning and from this event. I hope you will enjoy. So, coming from a tooling background, like what Vivek explained, so last it has been a 3 decade journey for me to learn, contribute to this field. So, I'm trying to put a bird's eye perspective about the future of tooling field based on my 3 decades of working and my awareness about the current industry. So, what strategic changes are happening, and what strategic strategies will be moving forward for particularly given the mandates which OEMs are making? Because when I say OEM here in the context is the behavioral nature of the customers who are buying the tools. So that's the in a nutshell understanding about OEM manufacturing here. So the abstract here is precision mold making is no longer just about cutting steel, and it is a critical driver for OEMs. You know, for OEM, any OEM business, whether it is in the aerospace, automotive, or electronic goods, or any industry, the backbone of that industry is the tooling field. So the tooling will define their entire, all their project future, existence, survival, all of these things. So now, given the industry in the era of Industry 5.0 industry, tooling is also evolving into a intelligent, data-driven set. It is, some design was made in the tool room, and then getting into the piloting, and then getting into the trials. That for linear model is no longer will not exist in anymore. It will now become a very circular, intelligent, real-time operating system, which keeps on responding to the needs of the industry. So we are talking about, basically what we are talking about is completely transforming the usability of the type. It's not just the mold life, it is the more the use. It is the usability of the molds to mold life to around 10, 20 to 30%, 50% in the entire use. So here, what we are talking about, the core strategies, what we are talking about is simulation-driven design and conformal tooling, and then tooling reuse. That means there is reviving the tools, and particularly when you are talking from mold making perspectives, then the hot runner walls are predominantly replacing into the mold construction. So here I'm trying to explain these core strategies on simulation-driven design and core conformal tooling. I will give you in a nutshell understanding about that. Of course, you can get into the literature and try to understand more depth of that. And then what precision machining excellence is happening at this point of a time, and tooling revival and maintenance. This is a completely new eye opener for tooling industries. There is a resource optimization is also very important, and then predictive analysis. So far, it was predictive analysis was more on general person or a tool room divided team based analysis, but now it becomes a global predictive analysis. That domain itself is shifting now. Then apart from that, the mandates that we aim is to move towards the circular economy, because the customers are mandated to move towards this sustainable circular economy models. So when the customers need is like that, when it is a mandate for them or a regulatory mandate, so obviously that translates into the tooling field as well. So tooling also has to be compliant with that. Then I'm ready to take some question and answers. So primarily what we're talking about the simulation driven design is, so what in simulation driven design we're talking about 98 to 99% of first pass yield. So the question of, so we're trying to make the tools at a confidence levels at 98 99% level of confidence means the number of trials, number of iterations, all of these things are shrinking out. Basically we are talking about manufacturing a tool and directly loading onto the production cycle. So that is the level of expectations and the practices that we have to now adopt. So primarily when we are talking about simulation design, we are talking about the stresses, we are talking about the deflections. We need to have a complete picture about the, when we have manufactured a mold, we need to know what stresses are playing into the mold and what stresses and what deflections are happening in the mold in real time basis in a running production environment. And then design iterations, because we are talking about, in if you are taking plastic injection mold design, the material what we are dealing with is a non-Newtonian fluid. That means the predictive levels are very scant. That means the material can change while, even while operating conditions itself. In operations also, in dynamically it can change. So it can shift its course of injection, all of these things. So in that dynamic scenario, you will also have to have a dynamic control on the molds. So that is the level of operational control that we are expecting on the mold itself also. It is not a physical mold and a, that I have made rigid mold and then it operates for everything. No, the rigid mold will not be able to operate for all of the conditions. It has to be a live, it should have some life like that. So any dynamic changes which are happening on the mold, on the life cycle of a mold, depending on that change needs, the mold also has to completely adapt into that environment. So then the next thing then we are talking about is digital twins. So that means when whatever design we have made, whatever analysis we have made, we have incorporated all of those things. Then simultaneously the data, the digital twin means the digital model along with the data, everything has to be live observed for monitoring purposes, for evaluation purposes, when the mold is also simultaneously operating in the shop floor. That means when a mold is operating on the shop floor, I should be able to understand what is happening in the design room as well. So conforming tooling means we are no longer, just cutting the standard tool channels, cooling channels and the cooling system we are designing. Here we are talking about, because of the advent of additive manufacturing, so we are able to make tooling, we are make cooling systems which are near, heat transfer. It is a reflection about the heat transfer profile of the mold itself. That means where the exactly precision, in a precision level, where exactly heat has to be removed at which point, exactly there we are able to design the cooling system there and extract the heat specifically. That means in a given profile about a parting line, there is a gradients of heat system itself. So that grade, according to the gradients itself, we'll be able to make a cooling channel at the cooling circular at the cooling system. Also, we are able to control at the flow level also. That means velocity also is controlled, at the discharge is also controlled simultaneously at the gradient level. That means it is a vector based calculations that we are making. So whether this fluid is circulated at input is at one point and extraction is at one point, but the internal circulation which is happening at the cooling level, that is very gradient based. So that we will be able to achieve using the conformal cooling techniques. So using these conformal techniques, we are able to reduce the cycle time reduction. That means 50% of the total cycle time itself is reduced, slashed. So when I say that given a mold which was made in the previous conventional routes and the conformal tooling mold, almost like 50% of the cycle time is slashed directly. So that also gives a dimensional stability in terms of issues like warpage, shrinkage, dimension, and the accuracy of the tolerances that we are able to achieve. Then we are talking about the strategies. That another strategy what we are talking, the focus is now on precision machining. So precision machining means we are now here, we're talking about tolerances like sub-zero level tolerances, like something like 2 microns level of tolerances we are able to achieve. We are requiring, as in day progresses, we are the requirements that we are getting now are at, so particularly at the critical dimensions, very stringent tolerances are expected by most of the AEMs. And when it comes to aerospace industries like aerospace and critical components on automotive components, the tolerance levels are sliding below the sub-zero level. So here the finishes are also very important again. So different functional parts will require different functional surface levels. So the RA level we are talking about are nearly micro finish, like 1 micron, 0.1 micron RA finish we are expecting on, which is, no, that means when we are talking about a machining with a RA level of 0.01, 0.1 means the one task which we were doing it as polishing is completely eliminated. That means from the machine itself, I should be able to get a polished surface itself. So almost like mirror finish parts. Then G codes. Because of the advent of the artificial intelligence today, we are able to generate G codes directly for each of these machines, and then also do the modifications that are required. And then we can. The one more big advantage about the artificial intelligence now is we are able to optimize the G codes. Now, when I say optimization, that means the machining time is completely reduced, and the potential errors which are there, or the potential vulnerable points which are there in the for the defect occurring at the machining level is completely eliminated. So we are able to make a very precise, and the best part of routine can be generated within minutes. That is the advantage with the AI adapted machining. Then in the industry compliance, when we are talking, in the industry compliance, like AS 9100 aerospace standard, or the 1649 IATF standards. So this ensures, that means in the previous we were talking about FMEA developing control systems, adapting, having a control chart, and then observing everything. Here we are trying to bring all of these knowledge into the upfront itself. Now that means all of these things can be taken up in the design stage itself, in the first iteration of the design stage itself, and then brought into that. That means this knowledge level is not feedback oriented, is upfront driven. All the knowledge base is already available. So we are trying to build a knowledge base, create a knowledge base there for every tool room. Almost is now creating this knowledge base now. So in the new part, which is a very focused important part, is the revival and maintenance. So this is a completely firefighting level so far what we have observed in the tooling industry. In the future, this is going to be a good portfolio of everybody's business. So here we are talking about reviving and the assets. The tooling assets which we are making will no longer be a standalone tooling assets. The usage and the ROI models will not be linear models anymore. These will be circular models, where a tooling asset once invested we will be able to recover that on multiple parts, on multiple modules. That means completely the tooling asset will be modularized. So apart from that, there is the 5 R's are there, which are there: reuse, then renovate, regenerate, respect, and repair. So all of these things we can able to look at. We have to look at on the tooling assets. So the life and the ROI which is generated, which we were expecting from the tooling assets, will now directly contribute something like 80%. It has to increase. the ROI has to increase up to 80%, and the scrap rates which you are generating from the tools, from these tools, has to be considerably reduced by almost like 40%. This we have already seen in many cases we have observed. Then the EDM efficiency, this is a very game changing happening in the from the advances which are happening in the machine tool control. So we are able to now see dynamic sparking. That means when we in the beginning we were having in the past machines or the past generation machines, we were having sparks. Once a spark and once a electrode is set into the machine, that's it till the end of the cycle. Here now we are having dynamic sparks and dynamic electrodes which will adapt to the each profile. So there won't be the requirement or the stress on the electrode will be considerably reduced. The electrode life also will increase because you are not operating at the same level of voltage and the same level of spark generating across the mold. Only where it is required you are using the high voltage sparks, and where where it is not required so much, we are going for the optimized level of that. Profiles are also becoming very beautiful here. The flexibility has increased. Then surface integrity, again, as I told you in the machining, here also we are able to achieve something like RA 1.1 micron level of surface finish. Again, with this kind of a superb sparking erosion techniques available, the requirement for the task of polishing, again, as an additional supplementary task, is completely eliminated. That means I machine the inserts and directly use them onto my mold and then onto the production itself. So that supplement task of doing polishing is completely reduced or almost like decimated. Apart from this, we were also in a traditional spark erosion, depending on the fixtures, need for the fixtures and the comfort of manufacturing, we were going for many multiple inserts assembled together. Now, with the advent of the AI techniques on the spark erosion programming itself, also we are able to consolidate them into the unified on a single monolithic inserts itself. When it says monolithic inserts, that means the geometry will become very, very complex. That means even there are some undercuts also, undercut surfaces are also there. We are able to go there, penetrate there, and then do the machining, EDM machining there. This eliminates the need for having multiple inserts and then assembling them together and then doing the matching. All of these things are completely eliminated. Even complex geometries at 5-dimensional machines, we are already operating multi-generation machine axis machines. Because of this, the inserts are now shifting into the mono block inserts. So now again, almost all the industries, all the mold manufacturers now in general have are all slowly moving into the hot runner systems. When I say hot runner systems, means here basically what we are talking about is the control what we are able to achieve at the point of insertion, at the point of flow, at the point of injection. So we are able to control the profile of the belt which is sent into the mold from the exit point of the nozzle of the machine to the entry point of the cavity or the impression in the mold. So here in this distance, we want to have almost 100% control on the flow profile of the material. That means where we want, how much we want, at what level we want, that much we are able to inject exactly into the point of the impressions where the component formation has to happen. So what is happening at this point of time when we are able to control at this use of hot runner systems, and the control we are able to achieve at the flow system is nearly 40 to 50% of scrap is directly eliminated. So almost like, except the flash and other small minimal wastages, the material is almost fully utilized for creating impressions on the component itself. That's one of the advantages. So, I'm not going into the technicalities of the hot runner system because it itself is a wide subject. Now, predictive analysis. See, as I in the beginning of the seminar, what I explained, molds are today's molds are not physical, just metal blocks. They are the value of the mold he is here in terms of the data it is happening. How much of predictive analysis I will be able to make. That means make based on the data which is available on the more than the value of the mold, the data of the mold is more value here now today. That is the where we are heading. Based on the how much data you are able to collect, gather from the mold, and then how much you are able to analyze that data, make the predictions, make estimations that will define the complete overall cost of the TCO of the tooling cost, whether it is on the mold maintenance, whether it is on the mold manufacturing, or whether it is on the mold operating, or it is the defects which is coming out of the scrap. All of these things to put together. And then the another significant advantage is we were able to make maintenance very informed decisions we are able to make because of the predictive analysis. We are operating, looking at the mold on a real time basis. Right now, I have a mold running on my shop floor, which is right now operating, whether it is at the second shift or whether it is at the morning shift. And the data which is continuously streaming into my laptop, and I am able to make a decisions there. In fact, the decisions are also prompted for me. I will not explore any decisions on any knowledge platform. The AI models are also suggesting what is the best course of action, what is the best course of control. In fact, my next two shift, how mold is going to behave, that also I am able to predict even in the early itself. So this is the level of control we are talking about the molds. Then circular economy, this is a aspiration which all the OEMs, that means our customers, what we are talking, who are heading towards, and there is a regulatory mandate for them also to go for circular economy and have a sustainable production systems. When they have their mandates, it obviously translates into the whether we want it or not. As a tier 1 supplier for a mold maker, it obviously translates all of their mandates into the tool room itself. So here we need to have modular die architecture. That means a mold manufactured is always a mold manufactured, is never on a shelf item. Then design for repair. That means all the mold should be all these parts and the elements of the mold we should be able to design, and we should be able to replace, and we should be able to. There cannot be a set of pin or a block or any item on a mold which I will not be able to repair or I will not be able to access at all. So everything has to be repairable. Then sustainable materials. The materials that we are using, again, which has to go towards the carbon neutral and decarbonization. So we have to minimize carbon-based release agents. All of these things which are there, which are the requirements or the constraints on the control constraints which are there imposed on the molding manufacturers. So that has to be taken care again in the mold design itself, and the tool makers have to take provisions for that. Then the key things that we want to let everyone know in this webinar is the mold life has to increase by 20 to 50%. What we are doing today and tomorrow that is a difference. The mold life has to completely increase. The cycle time, we are talking about 50% reduction in the complete cycle time. That means, cycle time is how much is required, only that much only is required. The additional luxury we were having will no longer be there, and the optimization that means we will run a luxurious life cycle, manufacturing cycle, and then start optimizing that's no longer there. We have to directly go to how much is required, only that much. Then first pass yield 98% means there is no trials, there is no pilot, all of these things are not there. I manufacture a mold, directly it goes to the production line. So that is the level of expectations that customers are having. And the tolerance levels, previously we were talking about 0.05, 0.05 microns tolerances we were talking molds. Now already most of the customers are already asking for 0.2 2 micron level accuracy. Many of the customers are already asking. Again, RA surface, because of the advent of the new machine tool technology, we are able to generate 1 micron level RA level. That means the polishing and the subsequent tasks which we were doing will be completely eliminated. So that directly from the machining table, I can shift that into the assembly and then start making the mold. So ROI recovery on the total recovery on the tooling investment we are talking about is beyond 80%. Beyond 80% we are talking. The uncertainty levels is shrunk. Previously it was at 50% level. Now the uncertainty levels are shrunk to less than 20 to 10% only the uncertainty. That means 80% to 90% we are talking about sure shots. Then the scrap reduction, as of now what we are having, current scrap reduction has to be reduced directly by 40%. Then electrode, because of the dynamic EDMs that we are able to have now, so the electrode, where making the electrode and then the life of the electrodes also have to be improved, which will definitely be included in the new generation machines. So let me give a conclusion. The conclusion is OEMs are transforming, tool rooms also have to transform. Tools have to be sustainable assets, and we as a tool room, any tool room making at the new generation level will have to, there is no chance we cannot be lagging behind. We have to go and start operating at a industry 5.0 balanced level. So we have to adopt the new technologies. We cannot be doing the same things what we were doing for the last in the legacy. Then the resilient systems, whatever uncertainties are happening, whatever uncertainties are expected, we have to be prepared for all the worst case conditions, worst case scenarios, the mold makers particularly.